The normal distribution. It's a bell-shaped curve, like you see there in the picture on the right, and it's a symmetrical curve, and the symmetry occurs around the mean. So if you'll notice, right in the middle of the red line, this is your X bar. In case you can't see that, I'll fill it in. Okay, so it's symmetrical about the mean. Okay, the area under the curve, you can see where it's shaded blue in the picture there. That complete area, the total area, shaded blue there, must equal to 1 or 100%. Okay? Let's see. Also, the area under the curve, when we compute the area, and that's what we're doing when we compute the probability using the normal distribution in our z-score. When we compute these areas, or anything having to do with it, really, the area corresponds to the probability. Okay, so the percentages you see will be a percent of a chance of occurrence, and we'll get into that with the examples. Okay, the baseline there, where I just, along the x-axis where I just wrote my x bar, that represents the x scores. Once we run that through the z-score formula, which we'll learn in a bit, they're standard scores in terms of z. So that's my data set along that line. So it's a continuous data set. Okay? Alrighty. Now, what I have here in this illustration, okay, is what we call the empirical rule. Now, you guys have heard that term before, empirical rule. Okay? And what the empirical rule just states is that within one standard deviation of the center of my data, so if you'll look here, let me get my highlighter. If you'll look here, one standard deviation out from my mean, okay? So here's my mean. Here I am. I'm going to subtract one standard deviation, or I could add one standard deviation. So within one standard deviation in either direction, that's where I have 68% of my data, okay? That's where 68%. So you see, this is the concentration of data, the dispersion, if you will, of data around the mean. Okay, within two standard deviations, so I can subtract two standard deviations or I can add two standard deviations. That's the next one out. We say that 95% of our data will be within two standard deviations. Okay? And then and we can go out to 3, and that's, of course, the further I go out, the more I'm going to be including in my distribution, right? In my data. The more of my data that the bigger the net I'm throwing out to collect my data. So we say 99.7% of data are within 3 standard deviations of the mean. So here's what that looks like, okay? We're really going to we'll say that within the 2 standard deviations, 95%, generally we say is pretty normal. Definitely within 1 standard deviation, 68% of my data, we can guarantee there's not going to, or we would guarantee it's higher probability that we would have no outliers inside of that interval, excuse me. Okay? So that's going to help us with our interpretations too. And we'll look at that in a little more later on. So we talked about earlier, when I started my lecture, I talked about comparing apples to oranges. If I want to compare 2 data sets, the classes, let's talk about the classes. Comparing 2 classes that you're taking. That's 2 separate data sets, and you can't really compare them. You might even have a different number of students. Different topics, of course. The tests may be weighted differently. Okay, so we need a way to standardize that so we can take a look at our scores and say, okay, relatively, how am I doing? You know, what am I doing better in, French or geometry, so to speak? So we need a level playing field, and that's what the z-score formula does, okay? So it takes x scores, x values, scores, data, scores. Let me put this way. Data values, when we see the word scores, X score, it's just data. Okay, we're referring to certain pieces of data. okay? In terms of x, the x values, it's not standardized, it does not have that level playing field that we need. So when we find the mean and standard deviation of a data set, we can use that to put the values that we want to compare on a level playing field. And that's what happens here. And that's the reason we had to know how to compute our mean and standard deviation. So, important formula here, okay? Right there. You don't want to forget this one. You definitely want to remember the z-score formula. It's incredibly important. Okay? And so, again, this puts the two data sets on a level playing field so we can compare them accurately. Okay. All right, let's take a look at some examples. Let me get those guys pulled up. Okay, one more important fact about the z-score. Up top we see z-scores. They're going to indicate to us how many standard deviations each data value is above or below the mean. So when we run our x-scores through the z-score formula with the appropriate information as well, we call it standardizing or normalizing. Okay, so we have a geometry test, a list of geometry test scores, 89, 97, 90, 98, 60, 77, 77, and 100 are scores from these students. So we want to know, first of all, let's practice this. What is the z-score for an 89? So we're looking at the 89. What is the standard score for the 89? Okay, first off, remember that the z-score formula here requires us to know the mean, right? Or your numerical average. And of course, your standard deviation. Okay. Alright, so I just kind of reminded you of the formulas down there in the left margin. So for the mean, we have to take the sum of the x values, all the scores. Okay, so sum of the scores and divided by the number of the scores in the list. So I've kind of begun using a little chart down here because that makes our standard deviation formula. If we're doing that by hand, it's a lot easier. So here we go. I go ahead and add down all the numbers down the list, and I get 688. 688 would be the sum of my x values. And how many x values are there? That's the next question. So there are 1, 2, 3, 4. There are 8 of them, okay? Alrighty, so remember, just make a little note that n is 8. So this will be 688 divided by 8 is 86. Okay, if you got 86, you're doing great. And let me just double check that. 866, oh, excuse me, 688 divided by 8 is 86. That's right. Okay, so we're going to hold on to that. Okay, we're not quite ready to put that in the z-score formula just yet. We have a little more calculating to do with the standard deviation formula. So remember, we're going to work our way from the inside out of that formula, okay? Let me change this to like a little thin blue here, okay? I'm going to rewrite my standard deviation formula up here near my table. Okay, I have the sum of x minus x bar square. All that's going to be over n minus 1. Okay, First, what I want to do is I want to take each x value in the list, starting with 89, and I'm going to subtract the mean from it. So let me make a column for that. Okay, we're going to take each x value, and we're subtracting the mean. So we're just doing this column first. Keep it simple, guys. Like at first, until you're really used to doing 2 steps in one. Let's keep it really simple. So we'll take it one thing at a time, one part of the formula at a time. Makes it a lot easier. Okay? So while I'm trying to do this, you guys start subtracting the mean, the 86, from each of these data scores. So we'll have first, we will have what? 89 minus 86. So that'll be your first one. Okay, then we'll have 97 minus 86. Okay, I'm going to count to 3, and I'm going to pause my thing while I finish filling all these in. Pause yours, because 1, on the count of 3, I'm going to have them all in there. 1, 2, pause your video, 3. Okay, so here's what you should have if you've done that correctly and subtracted 86 from each of these values. Including negative values, okay? You're not gonna end up with negative values. When we go to square these in the next round, we will be taking care of that. Okay? So what you're doing now, we're gonna want to add a column. Alright, let's go ahead and stretch this out. We're gonna add a column. I'm no Picasso today. And we're going to work our way out. So now we have the inside of the x minus x bars. Now we want to go ahead and square each of these values that we came up with, and then we'll add them afterwards. But so now we're going to have x minus x bar, and we're wanting to square it. So what we have in that second column that we just computed was the x minus x bars. So what we're going to do here is we're going to take 3 squared, which is 9, then 11 squared, etc., etc. So we're taking each value that we got and we're squaring it. Remember, when you square a negative number, it's positive. Okay? So let's, let me not do that. Okay, so now 4 squared. Let's go ahead and fill those in. You can go ahead and do that while I'm doing that. Find my bearings here. Okay. So we'll have 16. Yeah, 625. 25 squared, or actually negative 25 squared is also 625. I don't want to mix numbers up for you guys. So here we go. Alright, so here's my squares. Alright, let's extend that bottom bar, because the next thing that I am filling out here will be the sum of all my scores minus, let's see, x minus x bar squares. So that means you're just going to add up all this last column, the 9 plus 121 plus 16, etc., etc. So I'm going to pause my video for a minute on the count of 3, and then I'll be back with that summation. And I want you guys to maybe pause and try to carry out the rest of the standard deviation formula. Okay? Do it very carefully if you're doing that, but make sure you're writing with a pencil in case you need to erase. Okay? On the count of 3, I'm gonna, after I hit 3, I'm gonna keep going. So pause your video while I'm counting. 1, 2, 3. Pause. Okay, so you should have gotten 1,273 for that summation of x minus x bars squared. What this is the square. First, let me go back. Our first column that we added on, that second column, x minus x bar. This is how far each scar deviates from the mean. This is, in other words, the difference of each individual score from our average. When we square that, it's the square of the deviations from the mean. Okay? We call it standard deviation because if you think about what we're doing with the z-score, we're subtracting the mean divided by the standard deviation. We're basically standardizing, or we're getting an average deviation for the entire data set. It's basically what standard deviation is. And so here we go. Let's stick that 1273 in the numerator under that radical. Don't forget your radical symbol there. So standard deviation, I'm going to go ahead and make the answer space my fraction bar. So I'm going to have a 1273 divided by an n minus 1. Remember, n was 8, so that'll be 7. Okay? All right. So we want to go ahead and get that value, the 1273 divided by 7. 181.8571. Leave that value in your calculator, by the way. When we do this with Excel, we may be off 1 or 2 decimals, like 4n though. Okay, so we'll have 181. And I'm going to go up to 2 decimal places here. So we'll have 0.86. Extend my radical symbol. And now I'm going to take the square root of this. Now what I have so far is that the number 181.86, the unsquared version, is called the variance. Once we take the square root, we have the standard deviation. And that's the value. The standard deviation is what we use for future computations, what we need to have. Okay? Alright, so the square root of that is 13.49. 2 decimal places will be fine right now. My bearings. Where's my pencil? Where are you? Okay. Okay, so 13.49. Okay, so what I'm going to do here now on step 3, let me come down and below, like where I wrote the formulas there, up there in red, I'm going to go ahead and just notate, reminding myself what is x bar, what is my standard deviation. Alright, let's see, get my bearings here now. So we had x bar was 86, the average score 86, and the standard deviation, or the average deviation of all my scores away from this mean, 13.49 points away, was my standard deviation. Okay, so let's compute the z-score. Okay, so now what we were wanting, originally it's asking us, and it asked us this, what is the z-score for an 89? By the way, hold on to this mean and this standard deviation, because there's another part to this problem. This is the mean and standard deviation for this data set, always. So we can ask lots of questions on this, and you only have to answer the mean and standard deviation once. So let's go ahead and finish up. Let's find the z-score for an 89. So here's our z-score formula. Okay, we want to take that score of 89, we're going to subtract the mean of 86 and divide by our standard deviation of 13.49. Okay, so first, if you're using a calculator, clear out whatever you had before. We want to take an 89 minus 86. Press enter. And then divide that by 13.49. Okay, and you should get 0.22. So the z-score is positive 0.22. And for these z-scores, you're definitely going to only go 2 decimal places always for z-scores. That is a rounding rule for a z-score. So z-score is 0.22. And every decimal place that I'm writing here is important for the z-score. Okay, so this is how many standard deviations away from the mean. So because it's positive, we know it's going to be above the mean. Okay, if we get a negative z-score, by the way, I'm going to go ahead and talk about this right now. What are possible values or outcomes for a z-score? Because it's positive, we know that this is an above average score. Let me kind of scroll up, and you can maybe make note of this as well, right there with that z-score. Now I'm going to make that on the right margin, some little notes here, okay? This is important for z-scores, okay? So your z's are going to be somewhere between the -1, okay, and +1, okay? So anywhere in the negative, so it's, if it's left of 0, okay, remember that we had a normal curve, okay? Let me make it a little more symmetrical. Okay, it's something like this. One more try, okay? You try. Go ahead and try over there at home. Let me try doing it like this. Okay, that's close enough. So we said the center line, okay, is x bar. Okay, and so left of that, okay, and one other thing we also mentioned above was that for a standard normal curve, the mean is 0 and the standard deviation is 1. But we'll get more into that later on, but the center is the mean. By the way, because this is a symmetrical distribution, the mean, median, and mode are all equal. So look, let me make that little note. X bar is equal to my median, MD, and it's also equal to my mode if it would exist, okay? All the same, okay, and because this is symmetrical, the distribution is symmetrical. Mean, median, and mode are all equal, okay? And so we have that, and so to the left, my z-scores, the left of center, these are negative z-scores, okay? Negative z-scores. To the left. I put an arrow. And then to the right of the mean, or, yeah, the mean, the center, we'll have positive z-scores. So to the right, we have positive z-scores. Above average, in other words. So the negative sign gives us the direction to go in for my z-score and its location. Okay? Alrighty, more on that in a bit. Okay, so let's go on with this problem we're working on. So we want to know now, what is the z-score for a 60? Alright, let's get that. So I'm going to pause this, and I would like for you guys to find the z-score for a 60 in this data set, and then the z-score for 100. What I'll do before I pause it is I'll plug in the formula, the z-score for the 60. I'll just give you the basic formula. You can do the same thing for the 100, okay? And so here is this. So we would take the score that's raw, the raw score, subtract the mean, divide by the standard deviation, 13.49, equals. And do the same thing for the next little part. So you guys are working on this one and this one, okay? I'm going to count to 3. While I'm counting, you should be pausing your video, because once I count to 3, it's moving on. So you'll be able to check your work afterwards, but I do want you to try it. So on the count of 3, I want you to do these, finish this one, and do the next one. 1, 2, 3. Okay, here are my results for those two problems. The z-score for 60 is negative 1.93. If you look just below that, next to this asterisk here, let me try to highlight that. We'd say because of the negative sign, it would be 1.93 standard deviations below the test average. For the z-score for 100, we get 1.04. So it's 1.04 standard deviations above average for this test. Okay, so that's important to remember about the signs, negative or positive, gives us the direction above or below the mean or the average of whatever data set we're looking at. Okay, so we haven't really used it. We've computed it and kind of touched the surface, but let's look at part B here. Okay, here's another way. This is what I was talking about with comparing these two data sets, okay? Let me kind of try to give us a little more room here. Okay, so let's look at this. Amy took the ACT and got a score of 27. Okay, let me put this. Oh, wow, poor thing. Okay, so for her ACT, I'm summarizing my information here. For the ACT, her score, okay, so we'll say her X is 27, and she's got a mean of, what, 21? A standard deviation of 5.3. Okay? Stephanie took the SAT and got a score, okay, and so this is going to be Amy and her ACT. Now, let's go to the right there and make a little column. Stephanie, she took the SAT, all right, and she got a score, the raw score, right, it's not standardized yet, of 660, with the mean of 515, a standard deviation of, what, 116. Okay, relative to one another, we say relatively which student scored higher. So we can standardize these scenarios because we have our raw score, we have the mean and the standard deviation. That's all we need to levelize the playing field to compare these two data sets. We don't even need the whole data set if we're given the mean and the standard deviation outright. Yay, less work for us. So let's just get those z-scores in and see what we got, okay? Okay, and I'm going to call this for z, I'll call this z1, okay, since it's data set 1, okay? So we'll say this is z1. Okay, raw score x, 27 minus 21, right, the mean over the standard deviation, 5.3. You know what I really ought to do? I'm going to write out the formula just to help us remember it. Let's do that. X minus the mean, subtract the mean, divide by the standard deviation. It's really wise, guys. Just whenever you are about to use a formula, write it down. It helps you remember it, helps you learn it, seals it in your brain, good and ready for the test if you ever need it in the future. So, okay, anyway, let's go ahead and compute that. I'm going to count to 3, and what I'm going to do is I'm going to get you guys to do Z2 there on the other side for Stephanie's SAT. Now let's go ahead and write this x minus x bar over standard deviation. Go ahead and fill that in and find your solution, okay? And find the Z1 for me too. I'm counting to 3 now. I want you guys to finish these guys up. And we'll come back and we'll do the comparison together. 1, 2, 3. Okay, so in comparison to one another, which of the students really scored higher? Okay, we can see that Amy scored a 1.13 for her standard score, and Stephanie has a 1.25 for her standard score. So Stephanie did do better, but not that much better, right? Okay, they're both still within normal limits. You know, we consider maybe the average to be average interval of grades. So Amy didn't do so bad. She did fine. Anyway, this is how we use these relative to one another. Stephanie did a little bit better than Amy on her SAT score. Okay, as is the numbers when they're raw, we cannot legitimately say that. We have to standardize using the z-score formula. Then we can compare the two. All right. If you guys have any questions about anything, please let me know. Otherwise, please read this section in your textbook. It's very informational. If you have any questions about anything else, let me know. I'll probably post another video with just examples of each topic from this chapter. But if you need me to do that sooner rather than later, you need to let me know. You need to communicate. If you have a question, go ahead and get in touch with me. You know how to do it. All right. Talk to y'all soon.